Now we're going to talk about the instruction execution model that the processor presents. So the processor promises something that sounds a little strange. It promises that execution will appear to be sequential and atomic. It doesn't promise that it will be, but it promises it will appear to be that way. Now what does this mean? Well, sequential means that we execute instructions in order. So if I write a program that says instruction 1, 2, 3, sequential means that the processor will execute them 1, 2, 3, not 3, 2, 1. Atomic means that each instruction will execute all at once. This is easier to think about if you imagine a complicated instruction like multiply that may take many steps. This promises that all of those steps will be done before the next instruction starts. So sequential, here's an example. Program says do R2 equals R1 plus R2 first, then R3 equals R1 plus R2. The processor may not reverse it. It may not do the second computation first and the first computation second. And this isn't surprising. You'll get the wrong result in this case. Atomic, if the program says do this one first and that one second, what this means is the processor has to finish the first computation before it can start the second computation. So why do we care about this? Why would we care that the processor makes things appear to be in order and atomic? Well, the reason for this is we want the program to give us the right result. If we didn't have these guarantees, we couldn't understand what the program would do. If we don't know that the processor is going to execute code in the order we write it, we have no idea what's going to happen. And if we don't know that the processor is going to finish an instruction before it goes on to the next one, we don't know how it's going to work out. So these two guarantees are very important so we can understand what our code's going to do. Now, I wouldn't be spending a lot of time on this if this wasn't an interesting topic, and the reason this is interesting is that processors are neither sequential nor atomic these days. They break both of the rules, and they break these rules to get high performance, to run fast. And this is where appear comes in. So even though they break these rules, they still have to appear to be this way for the program to work. If they don't do that, then the code won't run correctly. So we're going to spend a lot of time talking about this when we get to pipelines, because pipelines are going to both do things out of order, and they're not going to do instructions all at the same time. And you're going to see how we have to fix up the processor to make sure this works. Another interesting part about computers these days is they're stored program computers. That means that the program and data are stored together in memory. Now this may not seem all that surprising, but many years ago, data and programs were stored in separate places, and still today on some high-end digital signal processors, you have separate program and data storage. What this means for processors today is that instructions have to be fetched from memory for execution, and data has to be fetched from memory for execution. So these are both the same, and indeed there's no difference between data and instruction memory. This makes computers simpler. You can have one type of memory and put everything in the same place. However, this is also why we get a lot of virus attacks. If you write over data with instructions, and then you execute that data, you can make code do stuff it wasn't supposed to do from the beginning. This is exactly what a buffer overflow is, and this is a side effect of having data and memory be the same sort of instructions. So let's take a look at the example instructions we have here in MIPS. And you can see that there are three types, and we're going to go through them and do some examples. So we're going to start out looking at data operations. We're going to look at addition and subtraction. Then we're going to look at data transfers. We're going to look at load word and store word. And then we're going to look at sequencing. We're going to look at the branch equals and not equals instruction, the jump instruction, and how you make loops out of these. So let's get started with data operations. Now to look at data operations, let's look in detail how they work with the processor. So we're going to take the model that we had from the previous lecture, where we had a simple processor idea, and we're going to make it a little more detailed so that we can actually see how these instructions execute. We've still got our memory where we're going to store our code. We've still got our register file where we're going to store the data we're working on. And now we have an ALU. This is an arithmetic and logic unit. This is where we do the computation. And now we're going to look at how we actually make code work with this setup. So the first thing we need is a program counter. That is a register that holds the instruction address. So our program counter is going to hold the address of the instruction we're working on, and then we need somewhere to hold the instruction that we're working on. So we use the program counter to fetch the instruction from the memory, and we put it in an instruction register. So what we have here is our program counter has the address, sends it to memory, the memory fetches the instruction and stores it in the current instruction in the instruction register. Now we need to do something with that instruction, and that's where the control logic is. The control logic is going to decode the current instruction, and it's going to tell the ALU and the register file what to do. The ALU is then going to execute the instruction. So it's going to take the data from the register file, do the computation, and then write the data back into the register file. The control logic has now finished the instruction, and now it's going to update the program counter to see what is the next instruction to execute. So this is the flow of instructions that this is the flow of instructions and data through the processor, and this is how the processor is going to work. Now let's take a look at some examples here. Here's an example of a program where we have two instructions. We're going to add R0 and R0 and store it into R4. So R0 is always 0. So this is the same as saying 0 plus 0 gets stored into R4. So R4 should be 0. Then we're going to do a subtraction. We're going to subtract R3 from R4 and store the results in R1. Now let's put some values in our register file so we can see what happens. Here we're going to put 6 in R3 and 4 in R4. And let's go ahead and start executing our program. So when our program starts, we start at program counter 0. This means we're going to access the instruction at memory location 0, and we're going to load this instruction into our instruction register. From our instruction register, we're going to decode what to do. We're going to tell the ALU what to do. In this case, this is an add instruction, so it's going to be an add. And we're going to tell the register file which data to fetch. In this case, this is an add instruction that uses R0 and R0. So we're going to fetch R0 and R0. We're going to add them together, which is 0 plus 0. And then we're going to write the results back into register 4, and so we get a 0 there. Now the last step is for the control to go in and calculate the next instruction. So since an instruction is a full word, that is 4 bytes, it's going to increment the program counter by 4 to go on to the next instruction. So now our program counter is 4. Now we can go on to the next instruction. So our program counter is 4. We're now looking at the next instruction. We read that instruction from memory into the instruction register. This is now a subtract instruction. The control decodes it. It tells the ALU it's going to do a subtraction. It tells the register file which data to access. In this case, registers 3 and 4. Registers 3 and 4 are loaded down into the ALU. It does the subtraction, and it writes the result back into register 1. In this case, 6, because we did 6 minus 0 equals 6. So what did we see here? Well, we saw that the program counter, or the PC, fetches instructions into the instruction register. The control then decodes the instruction and tells the ALU and the register file what to do. The ALU does the computation and writes the results back into the register file. And that's how we execute instructions.